This is Chapter 17, Sampling Distribution Models. Okay, please go ahead and open up your notes here to Sampling Distribution Models, class notes. Okay, let's go ahead and kind of define a couple things that we're going to be doing. We have defined these before, but I'm just going to make sure that you understand what these are. So first of all, a parameter refers to something in the population, some sort of population, like it could be mean, median, a measure in the population. So it could be mean, median, mode, anything, but it's based on the population. Statistic is based on the sample. Same thing, but based on the sample. Again, the same thing, these air quotes mean the same thing as above. This is why I always tell you PP, parameter, population, SS, sample, statistic. The population is who or what you are studying. And the sample is drawn. It's a smaller set of the population. Now the parameter, let me just remind you here, parameters and statistics, these are going to be, for the parameter, these are, my symbols are going to be Greek, and my statistic, are going to be English letters. For the most part, there's one exception, and I'll get to that. Okay, the population mean is the average in the population. And that symbol, which you've learned, is already mu. And that is a parameter. Population standard deviation is the average distance from the mean in the population. And that symbol looks like a little cursive O. It's a sigma. And that is a parameter. Now the parameters, remember, are part of our model. So when we do our normal model, we do mu and we do sigma. And that's what my normal model is based on. And then we put our sample mean in it to see if, so this would be mu here, to see how unusual it is. So the sample mean is, of course, the average in the sample. And that is X bar. And the 2.5470, that is from this data up above. And that is a statistic. The sample standard deviation is, of course, the average distance from the mean. And I'm going to just copy this to show you here. Copy. Oh. And this is the same thing, except instead of the population, it is the sample. And it is S, or you'll see it as SX. You'll see a little SX, SX, XY, standard deviation of X, standard deviation of Y, et cetera, et cetera. And that is also a statistic. Statistics, remember, are data that is gathered from my sample, and parameters are data that are gathered from my population. Okay, population proportion is going to be the proportion of success, you could say, right? Success, which you kind of have already talked about in binomial, in the population. And the sample proportion is going to be, of course, in my sample. Now, this is what I was talking about is your, in the population is your exception to the rule, how I told you all the letters are Greek that are parameters. Well, this population proportion is a parameter. However, it is P, and this is P hat. So when I see a Greek letter, that's a population. When I see an English letter, that's a sample, except in this case, when I see P, that refers to my population, and P hat refers to my sample. So, and I have a little saying that P wears a hat, see, P hat, when it is a stat. Okay, so this here is parameter still, and this here is a statistic. So with my model, let's just kind of look where we're headed. So as I said, we've got a normal model. I'll just kind of draw it on the side here, just a small little normal model. And let's say we have a normal model. We have our mean as P, and I'm going to just hang with me, believe me that this is a standard deviation, which I'm going to show you in just a second, PQ over N, or of course, remember Q is 1 minus P. So this is my model, and I'm saying, hey, this is what I am assuming to be true, that this is my model. And what you do is what we're going to be finding out here in a second is we're going to be taking our sample proportion, which let's say is P hat, and I'm saying, okay, P hat is here, and we're going to look and see what that percentage is and see is that considered unusual. So we're saying if P hat exists in here with P as the mean, then is this considered unusual? So I'm going to show you examples what exactly I mean, but that's kind of where we're headed. All right. So the problem is the reason we need P hat is because we don't know P. For instance, there's a lot of elections going on, and if you have Brown versus Smith, right? Brown versus Smith. And Brown wants to know how many people are concerned about a certain issue because they want to be able to be concerned about the issues that the people are interested in to be able to do better. Well, obviously, I don't know the population of Texas if I want them to vote for me. I don't know what the population of Texas believes, so I take a random sample, and that's when I use a proportion. So because we don't know our population, we are going to see we don't know what our population proportion is. So our population proportion is, remember which letter? That population proportion is my P. So I use P hat to estimate P for the true population proportion. P hat is for my sample, and I don't know what it is, so I'm going to use it to estimate what my population parameter is. I also, similarly, I don't know my population mean, and look up here, my population mean, remember, was the sample mu. So I'm going to use X bar to estimate mu. All right, so that's the same thing. I drew a P and a P hat here, but the same thing would be my mean. I don't know my mean. I'm going to use my sample mean. All right, so if you notice here, of course, I put here that my mean of my seniors, X bar is equal to 2.5470, and SX is equal to 0.7150. I could ask two different questions here. This would be one regarding my mean, saying what's the average GPA? This is all GPA with a 4-point scale in Howard County. And I'd say, what's the average GPA? I could also say, what proportion has, we could say, above a 3.0. And in that case, there's 100 here. And when I would go through and I would say, okay, let's see. If it's above a 3.0, we're just going to count, I'm just going to count the above a 3.0 here. Or I could say a 3.0 or above. I said above a 3.0, so I'm not going to include the 3 because I said above. So we're going to go here, 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 here. And real quick, just highlight everything above a 3.0. And let's see if I can grab them all. All right, I apologize if I missed any, but let's just go with the data that I am grabbing here. So let's count them up. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, so I got 28, and there are 100. So my P hat would be 28 over 100, which is 0.28. And as I said, my standard deviation, which we're going to learn here in just a second, the way you're going to do that is it's going to be PQ over N. So we'll do that in just a second, but I'm not going to, let's just table that for now. But anyway, my point is there's two different ways that you could do the data. You could do it quantitatively, remember when we did that? Where we're dealing with numbers and I'm asking average, mean, median, or we could do it categorically. And the category would be above a 3.0 or at a 3.0 or below? Yes or no? A category gives you like a yes or no answer. Quantitatively gets you something that I have numbers, that I'm able to find the mean, median, and mode. So there are two different ways to be able to represent data, and that's important because we're going to be going on forth with different types of tests. Okay, if I had chosen a different sample, next page here, and 100 different seniors. So these were 100 seniors I found in Howard County. If I said, okay, I want you to go to Howard County and find 100 seniors, you're going to get, which we've talked about, you're going to get, I would have different seniors, you're going to get a different sample. So therefore, you're going to get different sample statistics. However, it still represents the same population. And we know that a different sample almost always produces different statistics. So on a multiple choice, when you see the word same, when it says this one, interpret this result, and it says, oh, this gets the same or exact or things like that, you know that that's not correct because it's going to be slightly different almost all the time. Okay, so when we saw in this example on the previous page, calculate proportion of seniors that have above a 2.0, we did 3.0. We didn't do or higher, we just did above a 3.0 and record it below. We already did that. So we did p hat equals 28 over 100, which is 0.28. If I picked 10 other samples, let's say if I picked 10 other samples of 100 seniors, below represents the proportion of seniors in each group at a 2.0 or higher. Okay, so this here is doing the same thing. Let's just say it's above a 3.0. Well, it's going to get us some different data because we did above a 2.0. I could jump back there and see what we're going to get. Actually, let's just let it go. Sorry, because their data is going to be different. So we did above a 3.0, but look here. This is just saying, all right, I'm just going to I had 10 people go get 100 seniors, and this is the data they got. If you can notice that the data is really similar, but it's not exact. And it does have quite a bit of variability because you can see that the lowest one is 0.68 and the highest one is 0.83. But in general, it's within about 15%. So you're going to see here that when we have lower sampling variability versus higher sampling variability, we're going to have, does this have low or high, and how do I change it? When we have sampling variability where I have a very big difference, it's because we're comparing different samples and we're going to have different statistics. So we are going to see that I have low sampling variability when I have similar results and you have a large number of samples. You have a smaller number of samples, you're going to have a lot more sampling variability. Because when you start getting more and more data, you're going to see that when my N gets bigger, my sample size gets bigger, you're going to see that you end up getting that the results get a lot closer. For instance, if I take average on the test, let's look at your average on the test scores, right? And if I average them together, if I say, okay, I want your raw data and I want to see what you got on the test score. Okay, on the multiple choice, the low was a 30 and the high was a 110. That's a lot of sampling variability. But if I take the average score from each class, class 1 was like a 65, class 2 was a 72, another class was a 59, and another class was a 67. So you can see that when I found the average of each class, that the sampling variability went down quite a bit. Okay, and each individual, so the individual values are going to have a higher sampling variability like I just showed you. This would be individual values, and these are averages. And that is definitely going to have a higher sampling variability than the actual averages.
Should I let people in?
That's fine. Okay. So when you see here, let's look at this one here. We have a sampling model that consists of P1 hat, P2 hat, and so forth and so on. And there are actually more than 10 possible samples. We can have a bunch of possible samples. But this sampling model, instead of this one here, this question was, do you have a GPA higher than 2.0? Remember I talked about the two type of things? This one's saying, what's the average? Okay, so this one's saying this sampling model has an average of 0.754 and a standard deviation of 0.049. So we have an unbiased estimator versus a biased estimator, and an unbiased estimator is a mean. The statistic is in the model. So when you have a stat, an unbiased estimator is when a stat is used, and a stat is used in to estimate a parameter and it is an unbiased estimator. I'm just going to put UE, but that's unbiased estimator. If the mean of the sampling model is equal to the true value of the parameter. So what we're attempting to do is back here when I told you this here, I'm wanting my P and my P hat to be the same in my sample. That's the whole idea. So that's why when I look at here and I say, how unusual is this? If this is unusual, then we know that then there's something wrong with my population. So that's the whole idea. But we also see that if we have P equals 0.754, then we would have P hat would be an unbiased estimator because you can see it's the same. So if it's very similar or the same, we are going to say we have an unbiased estimator, okay? If it's biased, it's going to be very different. But as the sample changes, remember, so does P hat. So the closer P hat is to P, the closer we say that we have as a sampling distribution that has an unbiased estimator. Okay, so we can still have a statistic we can see here can be unbiased, but still have high variability. So, and variability is bad because if I say, what's the average, if I say I'm running again, the Brown versus Smith, I'm running against Mr. Smith and to be elected for a political office, and I have somebody that comes to me and says, oh, Ms. Brown, we have 70% of the voters are going to vote for you, and somebody else that says, oh, no, I got 50%, another person said 30%. I have so much variability, what do I trust? I have no idea what I believe. So to increase this, to avoid this, we're going to increase the size of the sample. The reason being is let's flip a coin. The probability of flipping a coin to be able to get tails is 50%. If I flip the coin 10 times, it's very likely that I could get 7 out of 10 tails. So if I just ask 10 people, I might get 70% like me. But then if or get tails for the same thing if I had a 50% also. But if I flip it 100 times, there's no way that I'm going to be getting 70 out of 100. I'm going to get something very close to 50 out of 100 because the sample size is much bigger and I'm reaching my true probability, my true population. Okay, let's go to sample proportions. Okay, so to describing the sample proportion, look, it's just a graph. It's either going to be like this or this or this and so forth and so on. So the way that we're headed is that we want a normal model, but this is what we have. So when we describe the sample proportion, we're using CUS again. Okay, remember CUS. Center, unusual features, shape, and spread. Same thing, okay? So we have here, let's look at our CUS and spread. When we see that our sample has an SRS, remember, is simple random sample of size n, then the following statements describe me for my sampling model for P hat. The center, we want the mean of P hat is what that means, is equal to P. P is my population proportion, and that's my center. So when I do here, this here is going to be P. Unusual features, which is my gaps, outliers, and clusters. We're going to, hopefully, our shape is going to be approximately normal. Why is our shape approximately normal? Well, you guys actually already learned this. We have a sample size sufficiently large. Does this look familiar? NP, NQ, remember Q is equal to 1 minus P, greater than 10. Remember we learned in our binomial distribution that if NP, NQ were greater than 10, then we have independence. And this is our assumption, and with independence, or excuse me, not independence, but we have approximately normal, I got the ones mixed up. I apologize. So this is the one we learned in our SPIT. Remember with binomial, with NP&Q, we could approximate our binomial to normal. And this is why, is because it is a normal approximation and we are able to go ahead and continue this. Now, if we have independence, right? If they're independent, we know that we have a spread that has a standard deviation, and I kind of alluded it to you. And you guys are going to see that this is actually on your formula chart also, is square root of PQN. If you guys look at the back of your formula chart, this is where you're going to see sampling distribution. And you're going to see this is exactly where you have mu p hat and you have square root of PQ over N. This is the mean and this is standard deviation. And you'll see there's a couple that we're going to start to understand and break down on this one, but it's on the back page. Okay, and we do have a condition, though. We have to have independence, right? And the condition, because it's sufficiently large, right, is that the 10% rule. Sufficiently large, 10%, right here. Remember that? We already learned that. And this is to show that we have independence. Okay, so let's look at our example here. We have, first of all, as I said, we have categorical data versus quantitative data, which the difference of categorical data, it's going to be usually yes or no answer, or putting in categories or something, and quantitative data is going to give me an average of something. So this one would be how many, what's the proportion if you have above a 3.0, right? And this would be what's the average GPA. The average GPA. All right, when I have a categorical data, I'm going to be using sample proportion. When I have sample means, I'm going to use quantitative. And that would be like using average GPA. So you're going to be using p hat equals P, and standard deviation equals PQ over N when I have proportion. And you're going to be using sample means when you have, when it's quantitative data, when it asks for the average. Something similar to this. You can see the example from the first page is I randomly select 100 seniors from Maryland and record the one's GPA. And here's just, then I had a bunch of people, I had 10 different people go out and get 100 samples, and this is the different samples they got. They all got 100 seniors, but they all got something slightly different. And this would be quantitative data, and you'd use the mean for this one as just, as you would see, you would use your mean here as your X bar is what you're going to be using. What does the sampling model, of course, look like? You're going to see the same thing, is that the sampling model for the means is going to be the same thing that we had. The difference here, you see the mean mu of X bar is equal to mu. And then you guys have, the shape is going to be, again, approximately normal. And this is for X bar. Sample size is sufficiently large. Now, this here, in order for the condition to be large, you see on this last one, we did NP/NQ. Well, P means proportion of success. For this one here, there's no proportion. It's means. So we don't have a P here. There's no P here at all. But we do have sample size. So for our large condition, remember way back when we did sampling experiments and observational studies, we used N greater than 30. Some textbooks use 40, but you are able to use 30. We're going to put this all into practice so you'll understand how to do it. But this is according to the central limit theorem, which is right here. And it basically says if I have a sampling model that is bigger than 30, then I can use normal condition. And so remember, this makes it be able to do my normal approximation. And the spread is going to be, the spread or my standard deviation is now whatever my standard deviation is divided by the square root of N. So you can see what happens to the standard deviation as N gets bigger and bigger. Well, when I divide by a bigger number, think about it, 1 divided by 2 versus is much bigger than 1 divided by 10. When I divide by a bigger number, I'm getting a smaller standard deviation, which is good because standard deviation means all my data, the average data distance is going to be closer to the mean. So the bigger the sample, the better. And so this condition, again, this is the same 10% condition, and that's my independence condition. All right, so to sum up here, I'm using a new, I know you're going to be super excited because I have a new wonderful word that I have, and it's RILT. So in order for me to be able to use my sampling models, this is what I'm doing. When I have proportions, when the sample is categorical and it's like a yes or no, what's the average proportion, we're going to use, it has to have a random sample, independent, and that the independence, of course, assumption is hooked into the 10% rule. These actually are going hand in hand with each other. And you can talk about them together. The large sample size, N, P, N, and Q both have to be greater than 10. So you can see really this here is the only difference of means. Since I have no, thank you, and since I have no P here, remember, there's no P for this one. For means, there's no P. You don't use P. You use sigma over square root of N, and for my large, oh, whoa, this is not right, sorry. This says, that's my standard deviation, sorry. This should be N greater than 30. I'm not really sure why that's there, but that should be just N greater than 30. Okay, so those are just my conditions, and I will show you how to apply it when we go forward from here. All right, thank you very much.